A very good morning to everyone. So today we are going to discuss about unit commitment. So what is meant by unit commitment and what is its significance we are going to discuss. So the word unit commitment, we are going to commit various generating units based on the demand. We are going to find out of the n number of units available, so which will be an economical combination of units based on the production cost. So that is what this problem of unit commitment refers to. So generally we have this along with another problem which is economic dispatch. So unit commitment and economic dispatch are twin problems which go hand in hand with each other. Like what is the difference? The question arises, what is the difference between unit commitment and economic dispatch? So unit commitment deals with finding the lowest cost combination based on the fuel cost. Unit commitment is more or less more oriented towards reducing the fuel cost of the plants. So and finding n number of combinations which will cater to this strategy of finding the lowest cost of operation. Whereas economic dispatch comes after unit commitment, or you can even say colloquially economic dispatch is a subproblem of unit commitment. Why? Because once you have found out the n number of units, so out of this economic dispatch tells you how to utilize the units, how to load the units based on the demand, dynamically varying demand. So out of the total demand for one particular demand we have found out n number of units. So for that same demand, how to use the units, how to utilize the units, in what way you can load the units, which unit you can load the maximum, which unit you can load the minimum, which unit you can load to half of its capacity among the n number of units found out by unit commitment. That is what is being discussed by economic dispatch. So both go hand in hand and both cater to the same purpose, right? So what is the significance of unit commitment? So the fuel cost needs to be minimized. So engineering system is not just about technically assessing the situation and using a technology alone, but finding a low cost technology or finding a low cost technique, because it involves cost. So the economics of power generation is a very vital aspect which every power system engineer needs to look upon. So here we have this optimization problem. So this unit commitment as well as economic dispatch both are optimization problems. So what is meant by an optimization problem? Finding a strategy or finding a solution which is optimal, means in the sense the objective has to be satisfied, that is the demand has to be here met out, the demand has to be met out, but at the same time it has to be a low cost strategy. So that is the constraint. So when you optimize a problem, that is when you achieve an objective by satisfying all the constraints also, then a problem becomes an optimization problem. So in that regard, both unit commitment as well as economic dispatch both are power system optimization problems. So now this unit commitment is finding the low cost strategy, that is out of n number of generators or generator combinations given their minimum and maximum loading limits, given their production cost and other details, which will be a low cost strategy, which combination of generators. So out of n generators you can find out some m combination of generators or m generators which will cater to this low cost. The overall production cost should be minimal. So that is what unit commitment refers to. If you are able to find out that n subset of if out of that n generators, if you are able to find out the m subset of generators which will operate at a lower cost, least cost, then you have done this unit commitment, right? So there are various constraints which needs to be taken into account. As I said that any optimization problem will always comes not only with an objective function but also with a constraint. You have to satisfy both the objective function as well as the constraint. So what are all the constraints in a unit commitment problem? We are going to see one by one. So what are all the constraints in unit commitment problem? The first comes the fuel constraint. Entire unit commitment problem is designed to revolve mainly around this constraint. We are so much concerned about this fuel constraint, the availability of fuel. So, based on the availability of fuel, you are going to find out how you can operate your generators, what combination of generators you can operate, because based on the design, each generator might require different amount of fuel. The turbine used in the generator, it needs to be rotated at a certain constant speed. So, for that you need either steam or water. So, for that based on that constraint you need the fuel. So, that fuel needs to be always kept in stock. So, that fuel constraint is very much a problem. So, unit commitment always orients itself towards satisfying this fuel constraint, which is of paramount importance. Okay. So, next is crew constraints. The personnel working in the power plant will operate in shifts. So, there must be always some crew, some technically strong skilled crew to cater to any problem if there is occurring in the power plant. So, this crew constraint, the crew availability is also a factor in unit commitment. Followed by minimum uptime and minimum downtime constraint. What is meant by this? So, once a generator is committed, it has to be kept on, it has to be kept commissioned for a certain amount of time compulsorily before it can be decommissioned. So, that is minimum uptime constraint. Likewise, what is minimum downtime constraint? So, once a generator is switched off or cut off from supply, there is a minimum time after which the generator can be recommissioned again. So, that is called as minimum downtime constraint. Before this time, you cannot again recommission the generator. Okay. So, this is also related with another aspect called hot and cold start. Hot start means a generator which is just now decommissioned, so that its dynamic aspects are still in operation, so that it can be recommissioned quickly, whereas a cold start refers to a generator which has been decommissioned for a very long time and it has to wait for another few amount of time, a small amount of time, so that it can be recommissioned back. So, you cannot rely on this generator, but you can rely on this generator for recommissioning, right. Next is spinning reserve constraint. So, what is meant by spinning reserve? The capacity, the generation capacity that is available over and above after meeting the load demand plus transmission losses. So, whenever a generation operates, it has to cater for not only the demand but also for the losses. So, apart from that, there must be some amount of additional capacity which is called as spinning reserve, which is readily available to operate, which is readily available to provide power if in case there is a sudden steep rise in demand occurs unintentionally. It has not been predicted, but suddenly it has occurred, the demand rise had occurred. That is very much possible in such a volatile environment like a power system. So, you also always have to have a spinning reserve, sufficient amount of spinning reserve, so that the dynamics of your power system are kept in place. So, otherwise the frequency of the system will drop, and in order to restore that, you need to send power through the tie line to the neighboring areas. So, which is again a complex process. So, this can be avoided by having a sufficient spinning reserve in that same power system, so that when there is a sudden rise in demand, this spinning reserve will take care of the sudden rise momentarily, right. So, next comes the must run constraint. So, certain generators, they have to always be kept in operation, only that will be economical since under certain aspects. So, it is a must run constraint, means the generator, certain amount of capacity should always be kept in operation. So, for a economical viewpoint. So, based on that, this must run constraint plays a very vital role in committing unit commitment. So, when you are committing units, these must run constraint generators have to be kept on. So, only from the rest of the generators you can do the unit commitment. So, you have to take this into consideration. The last comes the hydrothermal constraints. So, what is meant by hydrothermal constraints? So, our generation is not only just dependent on the hydropower plant or thermal power plant or uranium based power plant, it is based on a combination of generators including renewable energy based sources. So, if that be the case, there must be proper coordination between hydro and thermal power plants, because in summer season you have to operate your thermal power plant to the maximum capacity, as the availability of hydro based power plants will be very minimal. Likewise, in rainy season and winter season you can utilize this hydro to the maximum extent. So, this problem is called as hydrothermal scheduling. So, taking this hydro availability and thermal availability into constraint, you have to schedule your hydro and thermal power plants, and then you have to do unit commitment based on the available plants. So, unit commitment generally refers to the power plants which uses fuel, because it is its main motto is to optimize the fuel cost and find out some n lowest cost strategies. Okay. But you have to take these other factors also into consideration. So, these are the different constraints in unit commitment problem. Now, we are going to discuss about what are the methods of unit commitment. Okay. So, there are various complicated methods, you can even use modern optimization techniques, but today we will discuss one basic technique. We shall put into picture here 3 basic techniques, and from that we are going to discuss one basic technique. So, what are all the techniques? The first one is brute force method. The second one is priority listing method. The third one is forward dynamic programming. So, this method, last one is an algorithmic method. Okay. So, these are the basic methods of unit commitment. The first one is brute force method, so which find out the n lowest cost strategies by finding out the minimum and maximum combination of all possible combination of generators, and out of that what is the n lowest cost strategies. So, this is a very simple method. Next, followed by a priority listing method, which takes into picture the full load average production cost. We are going to discuss in detail with the help of a numerical problem. So, priority listing method takes into account the full load average production cost of each generators and find out the n low cost strategies with different combinations, right. The last one is the forward dynamic programming method. So, the first 2 methods comes in handy when the number of generators are significantly small, maybe some 10 to few hundreds of generators, but in a large power system you have thousands of generators scattered across the power system with various dynamics, different constraints, and you cannot manually calculate the cost function for all the generators in a stipulated amount of time. So, we come into the picture of having an algorithmic approach. So, this forward dynamic programming, it scans each generator by generator, takes in the values of the generator and calculates, and it follows an algorithmic approach of allocating a low cost generator out of n generators, and if the constraints are satisfied, it is moved into another subset of low cost strategies dynamically, each generator by generator. So, it follows an algorithmic iterative approach. So, you can also call it as an iterative approach. And based on that algorithm of dynamic programming, it finds the n lowest cost strategies. So, these are the three basic methods of unit commitment. So, out of which we are going to see about the priority listing method with the help of this problem. Right. So, what does this priority listing method do? It calculates the full load average production cost. You call it as FLAPC. You can call it as FLAPC of ith generator. So, I follows from 1 to n. It calculates this and arrange it in the ascending order of FLAPCs. So, how to calculate this FLAPC? So, here when we look at this data given here, we have been given the heat equation, heat rate equation for 3 generators here, right. So, it is in the form of a quadratic equation, and in the tabular column you have given with the fuel cost and minimum maximum combination of each generator. So, this is the fuel cost K, you can call it by name K. So, the fuel cost of ith generator multiplied by the heat rate of ith generator with the generation maximum divided by the generation maximum of that ith generator. So, this is going to be the formula for FLAPC. Kindly note down this. So, again I am telling, so you might have 1 to nth generator, okay. So, out of this you have to find out the full load average production cost, full load average production cost for each generator I to n. So, using the formula, so this Ki stands for fuel cost of ith generator, Hi of PGI max, it stands for, you have to substitute in the heat rate equation for that particular generator. If it is the first generator, you have to substitute, take the first equation. If it is the second generator, you have to take the second equation. If it is the third generator, you have to take the third equation, likewise, right. And then you have to substitute that maximum generation. Here it will be 600 for the first generator, it will be 400 for the second generator and 200 for the third generator, right. So, and this divided Ki into Hi of PGI max divided by PGI max, you have to substitute with the respective maximum generation for the ith generator. And again after that, what, this is the step 1. Next, what is step 2? You have to arrange the generators, rearrange the order of the generators in the ascending order of their FLAPCs. Starting from the lowest FLAPC generator, you have to arrange up to the maximum FLAPC generator. And then the third is you have to find the combinations. Right. So, again I am telling, first you have to find out the full load average production cost of ith generator. So, it will be Ki into Hi Pgi max divided by Pgi max. Please note down this formula, this is very much important. And then step 2 is arrange in the ascending order of FLA PCs. The third one is find out the combinations and strategies. So, with the help of this method, we are going to solve this unit commitment problem given here using the priority listing method. Generally in examination, if they ask you to solve using priority listing method, you have to use priority list method, or if any other method is asked, then you have to use that respective method. Otherwise, my suggestion would be you can use this priority listing method, which is also very much it gives you a closer unit commitment value, and also it is easy to solve from examination point of view, and you can get the answers very quickly. So, this method would be very useful, right. So, now let us go into this problem. I hope you would have copied this formula. Now, look at this problem. You have been given with 3 quadratic equations. You call it as a heat rate equation of each generator. So, in certain problems, they wouldn't have given this fuel cost, and they would have directly given the cost equation. So, you call it these equations either as H1, H2 and H3. If that be the case, you call them as heat rate equations. The other cases, you would be given 3 equations C1, C2, C3, you would call them as cost equations. You would call them as cost equations, right. So, if heat rate equation is given, then the fuel cost would be given, just like it's how it's given in this problem. You can see here you have been given 3 equations H1, H2 and H3. Obviously, the fuel cost for the respective units K1, K2 and K3 is also given. If in case they have directly given you the cost equation, the fuel cost would not be given. The fuel cost would not be given. So, while calculating your FLA PC, that is full load average production cost, you will directly substitute the cost equation. You will directly substitute the maximum generation in the cost equation divided by. So, this you have to keep very much clear in your mind. So, whether you have to first see, audit whether they have given the heat rate equation or the cost equation, they would have mentioned in the problem, right. So, if it is a cost equation, your FLA PC is directly you can substitute in that equation divided by this, all right. If in case they have given the heat equation, they would have definitely given the fuel cost, or if they have given the heat equation and they have not given the fuel cost, then assume fuel cost as 1 if not given. I will write down here, if heat rate equation given and fuel cost not given, then you can assume fuel cost equal to 1. Note down these conditions. Yeah. Now we can proceed with the problem. So our problem is a simple case where heat rate equation is also given and cost equation is also given. So we can directly substitute this and get the answers. So we can directly substitute and get the answers. So what does the first equation say? So the H1 is in the form of a quadratic equation, be it a cost equation or be it a heat rate equation, it will always be in the form of a quadratic equation in this form: AI PGI squared plus BI into PGI plus CI, where AI, BI and CI are coefficients. So first we can find out the FLAPC of unit 1. So what is the first, the fuel cost of unit 1? It is 1.1 into, you have to substitute in this equation. So what is the first equation? You have 0.0014 into Pg1 square. So in place of Pg1 you have to put Pg1 max. So it will be 600 squared plus you get 7.2 into again 600 plus 510. The whole thing divided by what is the maximum generation? It is 600. Likewise, you have to find out the FLAPC of second unit. The fuel cost of second unit is 1 into, you have to substitute the maximum generation of second unit, which is 400, in the second equation. So the first equation is completed. Now the second equation we are going to do. 0.00194 into what is Pg2? It will be 400 squared plus 7.85 into 400 plus you will get 310. The whole thing divided by 400. Likewise for the FLAPC of third unit, again now second unit of generation is over. Now for the third unit with the third maximum. So you will get FLAPC is fuel cost is 1.2 into 0.00482 into what is Pg3 max? It will be 200 squared plus 7.97 into 200 plus 78, the whole divided by 200. So based on this you can get the FLAPC of the first unit is, okay, we can write it down here, 9.79. FLAPC of the first unit is 9.79. The FLAPC of the second unit is 9.4. You can calculate and check for yourself. It is 9.4 and the FLAPC of third unit is 11.188. 11.188. So kindly check, verify whether you are getting these answers. So, next step is you have to arrange these units in the ascending order of FLAPCs. So, which is having the lowest FLAPC? It will be obviously unit 2, which is 9.4. So, this is going to be your unit and this is going to be your FLAPC. So, this will be unit 2 with an FLAPC of 9.4, followed by next is unit 1, which has an FLAPC of 9.79, followed by unit 3, which has the highest FLAPC of. The concept is FLAPC is have nothing but full load average production cost. When you operate the generator in full load, what is going to be the average production cost? So, the average production cost in operating these generators in full load is, one is 11.188, followed by 9.79, followed by 9.4. So, which is the lowest cost strategy here? Generator 2, as far as this problem is concerned, right. So, our aim is to find out the low cost. So, we have found out the low cost. Now, we are going to find out the unit commitment. You have to write it down. Okay, I will write down over here. So, when we want to use all the 3 generators, so we can write it as unit combination, okay, followed by minimum from that combination and maximum from that combination. Unit combinations followed by minimum from that combination and maximum from that combination. So, first will be 2, 1 and 3. You have to write in this order. This plus does not stand for addition, it stands for the combination order. So, first lowest FLAPC 2, followed by second lowest FLAPC 1, so that is the first generator, followed by the third generator. Now, if in case you have to drop any one generator from this combination, which it will be the highest cost generator, which is costing you more, you will drop that first, right. So, it will be 2 and 1. Again, if you want to drop one more generator from that, you will drop 1 and it will be only 2. Now, you have to find out the minimum and maximum combination from this. So, if you use all the 3 generators, the minimum combination will be 300, the maximum combination will be 1200. So, if you use the first and second generator alone, the minimum combination will be 250, maximum combination will be 1000. So, if you use generator 2 alone, the minimum combination would be 100 and maximum combination would be 400. You have to write down this. So, if the demand, you have to write finally, if the demand is greater than 1000, all 3 will be commissioned, all 3 will be committed. So, if the demand falls below 1000, 2 and 1 will be committed. If the demand is less than 400, only 2 will be committed. So, this is your unit commitment problem, solution to your unit commitment problem as per the data given in the problem. This is how you have to solve the unit commitment problem using priority list method when the heat equation or the cost equation is given and the minimum maximum generator limits are given and the fuel cost is given. So, this is the step by step procedure using a numerical problem of how to solve the unit commitment problem using priority listing method. So, hope you would have understood this. So, see you in the next video. Thank you.